for his hat.
I want to thank you all for coming back for the second round
Recent investment
of the desalination discussions. This is panel 2, and we're going to be talking about transforming water through the technology. This will kind of follow up on Jared's closing thoughts about how desalination is actually operated and owned. We're going to drill down into the specifics of the technology we've been discussing broadly, specific technologies, recent advancements and innovations, comparing technologies to one another, key technological advances from the past decade, and adoption of desalination here in the U.S. and beyond. We're going to start out with some comments from the panelists, a moderated discussion, and then a Q&A at the end. If you could come up this time to the microphone at the front, that would be great. Our moderator for this panel is Gary Wolf. He's the executive director of the Stop Waste Partnership, an expert in economics and engineering of resource use. Stop Waste is a publicly sponsored technical program that provides expert support and funding to prevent waste, conserve water and energy, and use resources more efficiently in Alameda County. He received his doctoral degree here in resource economics and his master in civil and environmental engineering from Stanford. He was the chair of the State Water Resources Control Board, member of the San Francisco Bay Regional Water Quality Control Board, economist and engineer for the Pacific Institute, and a professor of environmental economics at the Monterey Institute of International Studies. We thank him for being here today to moderate our second panel.
Thank you. It's a pleasure to be here. This is a very fun way for me to end my week since I don't do a lot of water work anymore. I run stopwaste.org, which is a government agency which manages solid waste, although in our work we do intersect with water agencies and water districts in a variety of ways. I do need to correct one thing in my introduction. I've never been the chair of the State Water Resources Control Board. I was the vice chair, but my chair then and my chair always is Tam Dodak. She will always be the chair of the State Board to me. We're going to spend 3 to 5 minutes each introducing ourselves and talking about the work that our organizations do, a few introductory remarks, and then I'll ask the panelists some questions and they will give incredibly illuminating answers, so much so that your heads will feel expanded and you'll feel uplifted. But don't worry, if you want to kill off those extra brain cells, there will be drinks afterwards. After that, we'll take questions from the audience and have, we hope, a positive dialogue. I was asked to make a few remarks at the beginning about the various basic technologies, if you will, for how to desalinate water. And because it's Friday afternoon, it's going to be a very casual sort of summary as opposed to a technical summary. And the other panelists, I'm sure, will speak more to some of these issues as they talk about the future and how what we do now can be improved upon going forward. The basic ways of getting fresh water out of salt water are either to heat it, freeze it, squeeze it, or do mysterious things with electricity. By heat it, I mean boil it, distill it. This is the most traditional form of desalination, multi-stage flash distillation, multi-effects distillation. In essence, you're boiling the water away from the salty water and then condensing it again as a fresh water. Sometimes that's done with a vacuum to assist in the boiling process. Sometimes it's done at an ambient temperature or pressure, but basically it's distillation. And this is used in roughly half of the facilities around the world, many of them in the Middle East where energy is inexpensive, and so boiling water is relatively inexpensive. The second way is freezing. Freezing is not used very much commercially, but you can actually freeze a salty water and then remove the ice off the top is mostly fresh water, and remove that and melt it, and you have a fresher water. This technique has also been used for distillation of liquor over the centuries. Applejack in colonial New England was a fermented apple cider in a barrel. You left it out on your front porch. At night it would freeze, and you'd go out there and you'd take the frozen water off the top and drink some of the liquid underneath, and then the next night it would freeze again, and over time the liquid beneath got more and more concentrated, stronger and stronger alcohol, because you're removing the fresh water off the top. Usually not a commercially viable process for saltwater desalination, but it is a means that can be used. The third one is squeezing the water, forcing it through filters of some type, membranes of some type. Reverse osmosis being the one we've mostly heard of, but there are all sorts of other techniques. And that is sort of the the emerging technology in desalination in terms of the actual commercial market. Most new facilities that are being built are reverse osmosis facilities. And some of the most interesting things that are going on are in membrane technology and in the costs and in the ability of membranes to remove salt at lower and lower cost or lower and lower pressure, which translates to lower and lower energy cost. And the last one is mysterious things with electricity. You may have heard of electrodialysis. It's a means for using electricity to draw cations and anions out of salty water so the water that's left behind is fresher. Electrodialysis is used in many small-scale desalination applications, but it has certain issues in larger scale applications which make it not so preferable, not so attractive. There are some innovations in that area. One that I'm somewhat familiar with is a company called Saltworks in Canada. They have this amazing technology where they basically use a pond of salt water which gets concentrated and become more salty, either using solar energy or waste heat. And then they have two other ponds of salt water where with connecting ionic bridges from the most saline pool to these medium level pools, you can allow only cations or anions to move to those secondary pools. Those pools then become charged, one positive and one negative. Then you have ion bridges that connect those to a raw water pool, and those ionic bridges only allow cations to move to the negatively charged pond and anions to move to the positively charged pond. And the final pond becomes a fresh water as a result of that. So it's a very low energy process. The technology that drives the whole thing is either waste heat or energy on the front end, and then the smartness that goes into building those ionic bridges, our ability to do magical things with materials related to a flow of electricity. So that's my little introductory spin to give you a sense of kind of the technologies that are out there, and if each other panelist can say something similarly fun, we'll have a great time. Let's just go down the panel, from left to right.
All right. My name is Slav Hermanowicz. I am a professor of environmental engineering here on campus. I have been working on different aspects of water quality engineering and management for quite a while. But because I'm an engineer, I chose to put up this single slide. And I'm not sure you can read it from the very back, but people on the left say no desal plants, whether people on the right say desal instead. And I think that, for me, exemplifies the very important issues that technologists, engineers like me, do not always realize, and that's the other side of the desalination business, the public perception, economics. And this is also where I'm getting involved. I want to see the applications of my research to be put into life. So that's pretty much about myself. I just wanted to add to our moderator explanation of Applejack that the same technology is used to produce very expensive ice wines where you concentrate grape juice by freezing it. So that's it. Jason.
All right. My name is Jason Holt. I'm the CTO of NanOasis. We're a early stage startup just north of here in Richmond, California. We're about 2.5 years old, and what we're working on is making a next generation reverse osmosis membrane. So next generation in the sense that incorporates nanomaterials into it. And the material that we're using are carbon nanotubes. Carbon nanotubes, for those of you not familiar with these materials, are essentially seamless cylinders of graphite. And people have studied these materials for decades now, have shown they have really impressive mechanical, thermal, electrical properties. But until very recently, no one had really studied their fluid properties, that is, how molecules behave when they're inside of these channels. Prior to NanOasis, I was a staff scientist at Lawrence Livermore Labs, and the focus of my research was on exactly this, understanding how water behaves inside these channels. And the findings of that work were that water flow in nanotubes less than 2 nanometers in size, extremely small pores, is orders of magnitude faster than in any other porous material, any other kind of membrane. So it's that characteristic, along with their extremely small sizes, that suggested to us it would make an ideal membrane, and particularly an ideal desalination membrane. 2.5, 3 years ago, we got the idea to start NanOasis, and the goal there is to try to commercialize this technology. The techniques that we used to make our prototype membranes at Livermore were very expensive and not inherently unscalable. So the task at hand in NanOasis is to take that innovation, that discovery of enhanced flow through these nanotubes, and to try to make it low cost and scalable. And the cost targets were pretty daunting. And the techniques that we used at Livermore to make our prototypes, the manufacturing costs were on the order of $1,000 per square foot. To compete with the competitors in the RO membrane field, we need to be at $1 a square foot. And so what that means for us is that we have to develop wet chemistry processes, methods that are similar to what's already being used in the RO membrane industry to produce these membranes. And so that's, we've been fortunate to receive a lot of investment along the way to help further our R&D, a combination of venture capital as well as some support from the DOE through a large ARPA-E grant last year, and we're just plugging away. So.
Thank you.
Hi, Andy Shea again with Acciona. I'll actually sort of take a little different tact. I'll be speaking from really sort of the practical application. And what we heard here actually is a very important part of our business, what I call the holy grail within the industry, and that is trying to drive down the cost of kilowatt hours per 1,000 gallons with the basic membrane elements, nanotube or other, while at the same time is maintaining water quality. And there's an important interplay there because we are dealing with elements like thermodynamics, and as I say, keep separating the boys from the girls. It takes a lot of energy to do that because they like to come together. Getting back to my teenagers, there are a lot of perpetual motion machines out there. Jared had made some reference to that, and at the same time is while that's kind of funny, it's not, because there are some important breakthroughs that have gone back to 1959. Dr. Sidney Loeb and some of his constituents and colleagues down at UCLA with some of their breakthroughs on the original RO membrane, and I understand that actually that delegation may have stolen some work from the folks at Berkeley, and maybe I shouldn't go down that path, but there's some bragging rights as far as who actually did develop the first RO membrane. But here we are, 30, 40 years later, talking about the same thing, and we're getting in this granular level. It's hugely important for our industry from an application standpoint. At the same time is we are dealing with the practical realities of the regulatory bodies, specifically the Department of Public Health, and their ability to understand the technology, and is that technology really creating a barrier against these pathogens that are in the water. And I think in the course of this session here, we'll talk about some of the permitting challenges and what that means as an impediment to these new challenges. But again, pleased to be here and contribute however we can.
Hi, I'm David Hansel. I'm the replacement venture capitalist. But it actually makes a lot of sense that I'm here. One, I've been a member of Berkeley for years. Two, I spent 12 short years on this campus. And after 20 years at work, I tried to figure out a way to come back here more often. And one of the ways I do that is I start companies out of the Berkeley campus, out of technologies out of Berkeley. The other reason is it was my partnership that funded NanOasis and Jason. So we've been deep in this. And last night in the movie Flow, about this many people were watching the movie Flow. I mean, it's sort of a bad news, good news thing. The bad news was that it was a 2-hour movie, and with the exception of about 4 minutes, it was all about evil corporations and social movements and things like that. And then the good news is there was one technical innovation, and it happened to come from Berkeley. It came from Berkeley Labs, which is why one of the reasons we start companies out of Berkeley. One, we like Berkeley. All of the partners in Exceed Capital are actually Berkeley alumni. And it's also the nexus of really most of the energy work. Some of the best energy work around is all being done here. So, and also, I think that there's a huge overlap between technology for social good and for capital creation. And, classic examples are you can make photovoltaics and LEDs, and therefore putting on houses or space shuttles or things like that, but they wind up lighting villages in Africa. Similarly, when we started out, the reason we wound up investing in NanOasis is we started with a water hypothesis. And we looked at lots of areas of water. We looked at agricultural water. We looked at high purity water for semiconductor manufacturing. We looked at food processing. And what we were looking for were a couple different characteristics. One was a market we were pretty sure was going to grow. I believe that reverse osmosis is going to grow no matter what. The second one was it was a technology that hasn't changed in a long time. Basically, the polyimide membranes, you're pushing water through something that's only slightly more permeable to water than it is to salt. And so we decided that reverse osmosis was the right thing. We looked around the United States west of the Mississippi and met Jason and some of the scientists working with him. And that was sort of the genesis of this. And I think that while conservation is going to do all sorts of wonderful things, the good thing about water and about energy, and realize we see water and energy as interchangeable, is that technology is going to play a big role. And one of the things I like about Berkeley, yes, it's got lots of Haas business students, it's got law students from both, but it also has a lot of engineers. And the combination of that's always been very powerful and interesting. And that's where we sit and why we fund experiments and corporations like that. The one last thing I was going to say is there's always a market risk. You know, how's that going to work? And one of the questions before we started on this company is we asked lots of desal plants, RO plants, and we'd asked the managers. We said, if we could make a better membrane and it had this specifications, would you use it? And it was one of the most enthusiastic market research studies we had ever done, because everybody said, if you could achieve those things, absolutely we'd do it. It's very important. And then we went off and funded it. You look Slav.
Good afternoon. Thank you for being here on a Friday afternoon. Everybody has a lot of better things to do, but you know the crowd is pretty good. I'm a chemical engineer. I've been in desalination for 28 years, designing and building plants. I was involved in Santa Barbara and hundreds of others. And I'm going to tell you a little bit about how we see this is going to be the nexus between the energy of the desalination, the cost of desalination, and some of the things going on out there. We have a problem, and let me define the problem for you. Is that about 8 or 10 years ago, entire water basins around the world, in Australia, in North Africa, in India, and in China, started running out of water. And it's a combination of not enough water, not enough rain, and too many people, population growth. At the same time, you saw the picture a few minutes ago. Andy showed us the picture of the Colorado River. But let me show you the numbers. These numbers are current as of about 3 days ago. The Colorado River has been dropping at Lake Mead at the rate of 1 foot per month. Right now, if you look at we went beyond the drought situation, and now we're about 6 feet away from the point at which the state will have to mandate rationing. 6 feet away, and we're dropping at the rate of 1 foot per month. Now, Heather mentioned that it's raining. It is raining. It is raining, and it did rain. If you look at here, 2005, it rained very hard, and then it kept going down. So it can rain, but we're drawing it. Basically, too many people drawing unlimited resources. And this is the source of water for about 30 million people. There's been a 20 million people population increase in Mexico, but that is what's going on. Now, the solution that was mentioned before is this is the old way to desalinate water. You basically you go to the vapor phase, you condense it, and it's very economical for doing high value products like whiskey. But if you want to do it in a big scale like this, you have to cascade it. You usually have about 10 many cascades, so it's very capex intensive, and it takes a lot of energy because you are changing from you're going to the vapor phase. So it's always going to take a lot more energy. Now, to give you some context, from a venture capital point of view, about 40 years ago, the biggest desalination company in the world was Coca-Cola. Coca-Cola decided, and talk about getting into a market early, Coca-Cola decided that this was an exciting market to be in, so they bought a company called Agua. So the Coca-Cola was the biggest maker of desalination plants, and this is a typical desalination plant in Saudi Arabia. Now, the way desalination is done today is you take seawater, you filter it, you pressurize it to 1,000 psi, and 40% goes through the membranes as your drinking water, and then you have about 60% of the flow coming out as a high-pressure brine. The brine comes out about 950 psi with the membranes we have today. If we get better nanomembranes, really the perfect membrane, it will come out about 650 to 700 psi. You still have to deal with the osmotic pressure of seawater. But the energy content, if the Carlsbad plant was mentioned here a couple times ago, the energy content of the brine in the Carlsbad plant is about 15 megawatts. So what do you do with that? Well, in the old days, you threw it away, and that's really what gave desalination the reputation of being a hummer. Desalination took a lot of energy, both in the thermal. You can see the different components of cost of the desalination. And if you go back to 72, it was thermal. Today, it's still about 70% of the plants being built in the world are thermal. And then seawater RO still took a lot of energy. So what we do today is we have developed a device called a pressure exchanger. We make it in San Leandro, which is about 3 bar stops away. If anybody's interested, you can come and talk. And it's very unique, because what we're doing is, let me go back one. We're recycling the energy, that 50 megawatts of energy, back to the membranes at 98% efficiency. and that 98% efficiency is so critical. To do that, we have to invent new material science, completely new devices and new material science. We have to invent a device that freewheels in water and spins and does the energy exchange, but it has to be very tough and it cannot corrode. So to do that, we have to develop a complete new family of materials made out of ceramics that don't corrode and 3 times tougher than steel, and that's really the perfect material. We have been, to give you an idea of scale, again, taking what I show you, the graphics, this is a big modern desalination plant. Those are the membranes up there. There will be anywhere from 20,000 to 50,000 membranes in this plant. This is the high pressure pump. This could be 1.5 megawatts of energy pumping the water to the membranes. And this is the PXs. You can see their array. The high pressure pump is doing 40% of the work. The PXs are doing 60% of the work for free. And that gives you an idea of what the technology is. So over time, the energy to do desalination and the cost to do desalination has come down. The typical plant out there, the ones being built in Singapore, in Australia, in Israel, they're coming in about 70 cents per cubic meter. Again, very metric. The acre feet that Andy was handling is not used outside of the U.S. So it's mostly metric. It's think of 1,000 liters. So it's $1, basically we're at 70 cents per 1,000 liter. Now, the cost of what people pay for river water, basically, is been going up. Went up with inflation, and then together with this water crisis, started to go up very fast. In San Diego, you're paying about $3 per cubic meter. I have a house in Monterey. I will talk about Monterey later. But I pay my marginal, if I use more than 40 gallons per person per day, goes up and then goes up, and then it goes up to $9 per cubic meter. So the desalination, and this is before desalination. So the desalination is really an affordable solution, because that was not true here. When people think of desalination, that wasn't true here. It was really very expensive compared to compare what people were paying for river water. Now, what we did with the technology, we were lucky to enter the market when there was a huge explosion in desalination plants in 2002, 2003 with the shortage. We grew the company very fast. The market grew very fast. We captured 70% market share in a global market. We did an IPO in 2008, and these are some of the plants, some of the plants that we have built in India, in North Africa, in Spain, in China, just about everywhere. Desalination is a little bit flat. Especially the building of these big plants overseas is a little bit flat for the moment, so revenue is a little bit flat. But if Global Water Intelligence, which is the source, same source as that Andy was using, is projecting by 2015, the demand will triple. And again, that's going to come from the fact that huge water basins in Libya and China will be putting in desalination plants, and hopefully eventually California. And as a company, what we're doing now is we did an acquisition of interesting company that makes freewheeling devices, very high energy recovery, very efficient devices that go at very high speeds. So we're in the process of redefining what a pump-to-pump water is, and how efficient it can be, and how fast it can run to make it smaller, and also on the other side to recover energy going to the grid. That's what we're doing, and I'll take your questions later.
Thank you. It was all very interesting. I'm going to go ahead and ask a few questions of the panelists to prime the discussion, and anyone who feels they have an answer is welcome to speak, but also you should feel entirely comfortable just passing, because there will be other good questions after, so everyone will have a chance to say some things. Let's start first with things other than the membrane and other than the energy recovery device we just heard about. What are some of the other things that can be reinvented in desalination? What are some of the other technological areas where breakthroughs are being worked on, other than membranes and other than energy recovery in RO plants? It's a tough question to start with. Please.
But I think the answer is just pre-treatment, but I may get back into membranes.
Let me
be careful on that one.
Yeah, but let me define why. In China, what they call seawater is really salty mud, and in Algeria, what they call seawater is salty sewage. So dealing with that with conventional pre-treatment methods is not enough. So you get pre-treatment is crucial.
And what types of things are being done in the pre-treatment field? What types of particular technologies or problems are people trying to solve?
To touch on Gigi's point is, you look at membranes or other as a separation process.
Yes.
So before the RO membranes are hopefully seeing clean seawater, you got to get the mud and use the term crap out of the water. Now, if it's the technical term, San Francisco Bay, there's a lot of stuff out there, organic material and other. It could be the Pacific Ocean. You could have harmful algal blooms. What the state will, as well as other agencies will do is require you to characterize that source water. Okay, there are wastewater treatment plants upstream, or there's a river that's dumping all sorts of organics down, and you've got to decide, well, this is under LT2, you got to have, under the surface water treatment rules, you got to have X levels of barrier in there. So in simple terms, you could have basically, call it a wastewater treatment plant, the sand filters in front of your RO system. That's, in essence, Tampa, but if it's not done right, it fails on you. Okay, I'm not particularly a big fan of sand filtration. Now we've seen the advent of, I'll call it high rates, I'll call it pre-treatments, almost clarifiers leading into really bad water. You could be having micro or ultrafiltration membranes in front of the RO units. So in the case of Adelaide, we've got submerged microfiltration units, one of the largest applications in the world, in front of the RO. So having a membrane on membrane is actually pretty cool, because it allows you to automate processes rather than having folks run around it's basically a big pool, the sand filters, and there's a lot of energy and manpower required for that. So in simple terms, we're seeing this Achilles heel of our industry, pre-treatment, being attacked pretty hard.
And is that attack primarily built around new technologies, or primarily around development of operational knowledge? That is to say, we've had sand filters for a long time, but learning how to use them in the right way to really protect an RO membrane may in fact be an area of learning. So is it learning how to use existing technologies better, or is it more a matter of new technologies in pre-treatment?
I'm somewhat laughing, because that's the problem that we had down in Tampa. The previous contractor, developer installed an inadequate system, two-stage sand filtration without proper chemical addition. We had to go in and retrofit it and throw in a polishing stage using diatomaceous earth, which is really called backwards. I mean, that's really a wastewater treatment technology as an intermediate stage. Yeah, I think there's a combination of good process engineering, and then you've got to ask the question, what is the facility supposed to be doing? If it's ramping up and down within a given week because of time of use rates that are being talked about for certain plants, sand filtration is probably not a good idea. The micro and ultrafiltration units are set up to basically ramp up and ramp down quicker.
One addition is, I think, that's coming from what Andy said. All these desalination plants are very complicated facilities, and you have to look at the energy use and chemical use and operation as a whole unit. So you need to integrate and optimize the whole system. I think this is also a very interesting area. Are you going to put more into pretreatment versus less recovery on your desal unit? What to do with brine? The brine management is a huge challenge. So if we're going to have any breakthrough technologies on the brine management, that would be fantastic. I'm not seeing anything on the horizon, but Berkeley is very intellectual and entrepreneurial, so maybe something's come up.
Something else that can be reinvented it's not membrane specific, but it's related to the membranes, and something that you need to do to take advantage of better membranes is to reinvent the cartridge design itself. So the cartridge inside of which you put 400 square feet of this membrane. That design is fundamentally unchanged in decades, and in order to operate at higher flux and the higher fouling that is associated with operating at that higher flux, we need to design solutions to change the kinds of feed spacers that are in place to mitigate the fouling that invariably occurs as you try to increase the productivity of a given element. Also, taking one step further away from that, looking at the pressure vessels themselves. These membrane cartridges are put in series, 5, 6, or 7 cartridges in series for new membrane modules operated at higher productivity. The optimal solution may be to have fewer of those elements in series to overcome these problems of, in the industry they refer to it as a thermodynamic restriction. You're operating at higher productivity, you could reach a point where the osmotic pressure at the end of that train is close to your applied pressure, and you're basically getting no product out of membranes number 6 and 7. So those are the kinds of non-membrane innovations I can think of, but intended to kind of take advantage of improvements in membrane design that are coming down the pipeline.
And actually, I think you said both improvements in membrane, in the design of the cartridges as well as the membranes, but also I think in your answer you also were suggesting that the manifolding going to and from the membrane, to and from the cartridges, the way they're laid out is an area for innovation.
Yeah.
Is that right? I believe I read an article last summer about the new desal plant in Perth, and they're claiming that it'll be use 10% less energy because there's a new manifolding technique for the way the cartridges are laid out. It's an example of the sort of thing you're talking about.
I mean, there's all sorts of things. Certainly, pre-treatment and ways of keeping membranes from fouling. There was a Clean Tech Open winner where he had it on a giant turntable to use the Coriolis effect to do that. There have been like Jared in the last panel, as a VC we get lots of people with ideas. There's a lot of people trying to capture, to reduce the external energy requirements, so they're capturing solar and trying to put it in conjunction. And it basically comes out as a wash so far. But there's a lot of work done in surfaces to keep things from fouling, to kill bacteria, using different compounds, using shapes of nanostructures and things like that. So people identify small niches of the problems. How can I make it chlorine resistant? How can I kill bacteria? How can I keep it from fouling? And there's all sorts of inventors out there trying to attack each one of these problems.
Let me mention something that hasn't been mentioned before. In the Monterey area, the big push was for the Moss Landing plant with the open pipe and the impingement and entrainment, and probably the one that's going to win it, which is the waste done in Alicante in Spain. In Monterrey, we have like 20 miles of sand dunes all the way from Moss Landing to the aquarium, pretty much. And so they're going to put, probably at the marina plant where they do the hang gliding, they're going to put some beach wells. And when you do that, you get rid of the impingement problem, the entrainment problem. Also, you don't have to deal with the red ties that come in every few years. And the operation of the plant is a lot simpler. Now, the problem with that is that you cannot do it everywhere. You need a nice sandy dune area, and also it wouldn't work for a massive plant like the one that Acciona is building in Melbourne, right? Adelaide. So it wouldn't work because you would take a huge amount of beach. So, but it works for smaller plants, and it is a solution.
Thank you. I want to ask about the economic side of it, if you will. And let's start with our venture capitalist representative. But anyone else should speak about the economics too as we get into this. From a VC standpoint, what's the investment thesis around desalination? How does it compare to other water investments? Why are you investing in desal versus something else in the water field, which is a very exciting field now? And what do you want to see if someone comes to you, with I've got this invention advice? What are you looking for in an advance that makes it worthy of investing in?
As I described earlier, there's the market risk, and that's really the trickiest one for us, is if we build it, will people pay good money for it, and will we make money on it? And probably the easiest way to check that as best you can is to call up operators of desal plants and ask them, what would you pay how much for? Now, that's not a guarantee for it, but we were looking at things, we were looking at something that was going to plug and play. So we're looking at a cartridge that will go right where the cartridge is right now. We were looking at what was the biggest cost, and just like Gigi found, there's a huge cost of energy. So how could we increase productivity without, increase productivity at the same energy or whatever? It's a trade, but you're going to get more for it. We discarded, a lot of the markets were too small, markets such as semiconductor, ultra high purity, and they were already very well served and more dispersed. We look for a market that either is rapidly growing, and we actually believe eventually that desal is going to be rapidly growing, or that there's sufficient turnover where new players come in and old players get replaced so that a small startup would have a chance of gaining some significant market share. And so in terms of the technical risk, as long as it doesn't violate any of the laws of thermodynamics, then it's worth a fair shot. And if we can determine whether or not it will work within a reasonable time and capital efficient method, which Jason and his team did, that's how we decide what to fund and what not to.
So you basically see the desalination field growing and felt that there will be businesses building plants, so you're going to look at marketing to them, devices they would
and the
buy.
cartridges get replaced. So there's a replacement market, so it's a razor blade market, and I don't have to build the razor, somebody else can do that. I really just want to be selling better blades. And so I didn't have to worry. A lot of, if you're making photovoltaic cells that last 20 years, you have to have brand new plants being built. And that's a more difficult economic plan to make. But there's a steady turnover of cartridges.
And to that point, Gigi touched on it a little bit. We've been, our first generation desal plants in the Canary Islands are almost 30 years old.
That's right.
So we're in the third generation of membranes. Well, guys, you got fourth and fifth. We're waiting for them. Come on out. And again,
how big of an improvement was it between the first and third?
Oh, I'll have to defer.
Probably in energy about 15-20%.
Yeah.
And we've been focusing on desal, that's membrane separation. A lot of the stuff could also apply to reuse. Let me throw something in the mix here. Direct potable reuse specifically. So again, if you can unlock some of these elements, no pun intended, on the seawater side, you may also be able to do it on the wastewater side to the satisfaction of the governing bodies. And of course, that opens up huge opportunities going forward.
Right. Any other comments from the panel?
One thing I would add again concerning investing in water. Not that I'm a venture capitalist, but I could see if I was in David's shoes, not all VCs see water the same way. I think there's clearly a huge market, 6 billion thirsty people out there, but I think it takes the right kind of venture capitalists to place their bets here. Investing in a membrane company is not like investing in Facebook. So that's fortunately I think there's a growing trend that some of the larger tier VC firms are establishing, they have green funds and they're realizing that, water needs to be a part of that portfolio.
Water's an outlier for venture.
I'm sorry, water's what?
Water is an outlier for venture.
An outlier
There
for venture,
are
yes.
almost no venture plays. There's a handful. I mean, when you compare it with photovoltaics or with wind or
Yes.
smart grid, I mean, not even going to social networks. Water was a hard nut to crack. There are very, very few venture plays. There are even fewer investors willing to do it. And there's been, in the last year, there's been an appreciation in the venture community, which is good for us, that, wow, this is important, and we will be invested in it. But when we, started on this endeavor, there were 3 companies, right, and 3 investors. It was about it, which for around here is a pretty small number.
When was that? I mean, about how far back was
2007.
that? Oh, 2007, okay.
Yeah.
In the last few years, I mean, I've heard a lot of interest. You'll see at VC conferences, there's typically a panel on water. I mean, there's 5 panels on energy and,
there's
so
no
forth.
investment.
But there's still some amount of panel on water. I see, but people aren't actually investing, you're saying.
Yeah.
They're interested, they're listening, but not finding anything attractive enough.
Yeah.
Well, as an outsider to this, but having talked with a lot of my friends in VC, I think it's even bigger problem with financing, especially larger projects, and that's a really lack of knowledge by investors. If you look at, say, private equity firms, they look at the asset allocation classes, and this is dumped under infrastructure. And infrastructure is for them anything from bridges to prisons to roads to water. And so I think there's a lot of need to educate the financial community, larger financial community, in the possibilities of investing in water, which has its own perils, as everybody says. Usually requires a large amount of money. What's your investments? Are probably in tens of millions of dollars.
Well, I mean, we're a small fund, relatively small fund, and before 2008, we could invest in projects that would require a lot of capital because there were non-equity ways to finance things. That's gone away, largely. And notice I said 2007 is when we made this investment. But some of the financing decisions have changed after the fall of 2008. But making membranes themselves is a constrained size, so it wouldn't require hundreds of millions of dollars to get off the ground.
Thank you. It's all very interesting. I think now we should open it up to the audience. Do we have any questions from the audience here in the front?
Just one quick question. It seems to me like in many situations that parabolic solar thermal, because of the pressure and the heat, would be a great thing to add. Is it being done much? Is it realistic?
Parabolic troughs?
Yeah. You get pressure, you get heat. And you probably need both of these for a lot of these processes. I'm looking at heat.
You make more money by running a steam turbine and selling electricity at 8 cents a kilowatt hour, if you make it. And the solar thermal plants are a plumber's nightmare, right?
Yeah.
Osra came here and
Yeah. Also, let me give you another. To do solar desalination, you need a couple of things. You need to be close to the ocean. You need a lot of sun, and you need the sun to be reliable. You need to be fairly warm and whatever. That's called a resort. So whenever you have those conditions,
or Israel.
Whenever you have those conditions, real estate tends to be very expensive. So in the Monterey area, there are no wells at least minimum, $500,000 an acre or something. So when you start doing the numbers of solar desalination, the load on the plants, the numbers come out. You're better going to the Mojave Desert, doing what you just mentioned, and then transferring the energy to the grid to do desalination just in a very small footprint, like they're doing in Carlsbad along the coast.
But there are a couple of points there, and then, one of which is, don't forget the thermal solar plants require a fair amount of water. It's a thermal cycle.
That's right.
So as an owner and operator of the Nevada Solar One plants, I'm kind of embarrassed that we're, have a water footprint. But that's just the nature of that thermal cycle. So, could you have, hypothetically, a plant in the Mojave using brackish groundwater? There may be some solutions going forward, very site-specific. But that is, what of this interplay between water and power.
Interesting point.
I'll take a slightly different tack on this, because when we talk about desalination and we talk the universe of desalination technologies from thermal and so on, we focus on energy, and that's the right focus, but we should also focus on what is known as the quality of energy, and the thermodynamics know it as exergy. And essentially what it is that you can convert electrical energy into any other form of energy very efficiently. You can make a heater, you can make an engine. However, you cannot take low-grade heat, for example, at the temperature of 35 degrees centigrade, which is going to be, 100 degrees Fahrenheit, and convert it very efficiently, say, into electricity. You can, but it's very inefficient. So there are a number of technologies that use a lot of energy, but they use low quality of energy, or potentially can use low quality of energy. One that is coming forward is something called forward osmosis that can use, at least according to their inventors, very low quality of energy, although the amount of energy is not so small, as opposed to reverse osmosis that uses less energy, but you have to pump it, you have to deliver mechanical energy. So that issue of the quality of energy may play in a solar setup, because that's the low-grade energy, but it's for free. So again, it's not a silver bullet, but it may have a part in the portfolio.
We have 3 people here in the third row, so we'll take on the left, then coming to the right, the woman with her hand up, and then we have a woman over here.
So in the earlier panel, we talked about some of the environmental aspects of desal, and one that wasn't mentioned is, it seems, if what you're saying about 50,000 cartridge units in a facility, so there's a lot of cartridges, and I imagine they're made out of stainless steel or plastic, carbon, some kind of vortex-like membrane, different kind of membrane. So, thank you. So, what's the opportunity at end of life for recycle, reuse, and as producers of all those RO filters, I'm wondering, or dealing with RO filter producers, are you guys concerned about kind of the end of life piece and how they can be not just, end up in landfill, but actually maybe even a producer take-back protocol? That's something you guys are seeing, thinking about?
Well, one aspect of it is make it last longer. So understand the failure modes, and try when you design a new product, try to push those off. And failure modes are fouling and things growing on them, and current membranes are not very resistant to some ways of sterilizing and things like that. So I know what we're thinking about is making them last longer, because that's of value to our customers. They told us that. And
Did they tell you that they would like you to take them back when they're no longer usable?
No.
You're talking about regeneration.
Yeah.
I mean, in many sense, you're constantly regenerating.
Yeah.
Because of backwashing and cleaning protocols. I mean, that could happen every 3 to 6 months. If you get hit with a harmful algal bloom, that could be not every day, but pretty darn close, because you develop the slick on it.
Yeah.
But you got a couple issues there. Are you sliming over the membranes? Did you throw in some ferric salts, from the pre-treatment that got in there and totally trashed the membranes? I mean, what's a bad day at an RO plant? It's 10,000 membranes going up in smoke, basically. That's $6 million. And yeah, that's a solid waste nightmare.
Yeah.
At the same time is, there's, if you didn't damage the membranes, can you put the heavy load on, that's on the front unit and then shift them around? I mean,
Yeah.
and then you're trading off labor, versus just replacing the $500-600 per element. We've heard some units go from seawater duty to brackish water duty. and sort of regenerated. So there is an element of recycling. At the same time as if you're in that 5th or 7th year, these things have been pounded on, physically pounded by the water hammering in these plants. There may not be enough structure left.
Getting to a comment that David touched upon, what we're working on the membrane side is to choose, work with other kinds of polymers that have not been conventionally used for making these membranes to make them chlorine tolerant specifically. That's the people we've talked to in the industry said that, high flux, higher productivity would be great, or if you could reduce the energy 10-15%, that'd be great. But if you could also make it chlorine tolerant, that's the holy grail. The industry, making something that can withstand the few ppm worth of chlorine needed to mitigate biofouling. And so you don't have to now chlorinate, dechlorinate before it hits the RO section and then rechlorinate the product water at the end. You can expose your RO section to the dosage of chlorine
It
needed.
sounds like there's techniques for lengthening the life.
Yep.
But ultimately, potentially, like all the solar panels going up, after 40 years, 20 years, 50 years, whatever time period, they're going to end up in landfill unless we work out a way of running them or reusing them. So I guess as an innovative new startup, I'm curious, just in your thinking, and as a VC, are you thinking about investing in companies in this space that are concerned about end of life of that product that is helping all the way along the chain?
I mean, the brutal answer is no.
Okay.
Yeah, we try and make it longer. My job is actually to make money for the limited partners, and limited partners, could be university endowments, and so no. And I actually got into recycling membranes on a totally different. This is hemodialysis, and there's a much higher turnover of an order of magnitude, several orders of magnitude more membranes. More strictly regulated, and it didn't turn out to be economic either. Although land waste, that's a much bigger problem for that filter application.
Yeah, when I started doing this, you were lucky to get 3 years. You were really lucky to get 3 years, and you're probably getting 7 years in the big plants. And they're phased out in phases. You're changing 1/7. So I think the membrane life is getting better. I think it can get a lot better. That's one of the reasons why you saw the cost coming down, because the members are cheaper but also a lot more reliable, and the know-how is more widespread.
I'm going to interject a comment here and then move us on to the next two questions. The comment is, I mostly work in the solid waste field now, and we have similar problems with packaging. 40% of the municipal waste stream is packaging, and you go talk to packaging designers about it, and of course they're interested if they can come up with a product that's recyclable, end of life, or reusable. But the main drivers are protecting the product and transport. Product loss drives the economics of the packaging decision more than anything else, and after that, product aesthetics at point of sale drive it as well. So, the reusability at end of life can come into the design process, but it's a lesser criteria than any of the others. And so finding some way to get that into the process is more a government and regulatory issue than a way to make it work from the designer perspective. I actually asked this exact same question about the cartridges in a desal plant that I toured in June. And the operator, the outer layer of the cartridge is a plastic, which is recyclable, but the plant is in Perth, Australia, and they didn't have a place to recycle it locally, so they need to accumulate enough cartridges to have a load to ship someplace far away, where the cartridges get broken open, the membrane removed, the outer cartridge ground, cleaned, and recycled. And so they're just logistical issues as well for some of the locations of the plants as compared to the industries that can, in fact, use the materials. So we have two more questions here in the second row, and in the interest of time, if you can do short answers to these questions so we can at least get these two people in.
The professor began his introduction with kind of the emotional side of desal, pro and anti. And it certainly arouses a lot in kind of this civil society. And our recent experience in Marin, there were a lot of concerns of environmental health, human health, and of course the economics. So I'm kind of concerned as we're talking about the growth of desal, if what you see, the impact of kind of societal concerns, and specifically for Andy and Gigi, what portion of your budgets go toward lobbying or PR to kind of set a pro
Free shoot.
Yeah. Okay, I'll take it first. Yeah, we probably spend about 10% of our budget in marketing in general, promoting desalination and just the concept. We don't do lobbying in California because this has been actually a big market for lawyers, not for desalination so far. I was involved in the Santa Barbara plant 20 years ago, but there hasn't been a big plant built since. So it probably will happen in a couple of years from now, and then when it's closer to the that graph that you saw that is going to hit 6 feet down, when that happens, I think to start doing lobbying, because then people need to find solutions. But right now, people are not they're worried about the budget, they're worried about Jerry Brown coming on board. They're worried about many things, but they're not worried about the fact that in places like Australia, where the same thing happened, it started to happen 10 years ago, when they got to the halfway point, they started to recycle, conserve, or do re-educate the public, educate people, give hourglasses so people could time their showers, do many things so people start conserving water. So you don't allow it to go so far down, because it gets to a point that then ration is the only solution, because it takes, even if you permit Carlsbad today, it's going to take 3 or 4 years to get it going, and you're going to be out of water before then.
So let's move to the next question. If
Well,
we could.
just briefly, I'm a little bit horrified by some of the misconceptions on desal. I mean, you cannot be putting out bad water into the system. The Department of Public Health won't allow it. You cannot be contaminating the bay. Tam and her organization can't do it. Won't allow that permit to go. For our organization, we're all advocates. I mean, nobody is specifically lobbying Jared. Now, that being said, there are associations being formed. Cal Desal has just been formed to help demystify some of this. Water Reefs Association I mentioned. Gigi's been a leader at the International Desalination Association. So there are organizations out there that you could say lobby, but not specific individuals or members of Congress, because it's all local. I mean, it's all local.
So we'll go to the next question with the caveat that we all know that regulatory agencies never make mistakes.
Yeah.
Next question.
I have a question about developing countries. How big of a market is desalination in developing countries, and how much can this market be covered by distributed technologies? Like I've seen designs for water cones where you can use basically solar energy to produce small amounts of water, or fog particles in the water.
Well, maybe I'll take a crack at that. Well, I think potentially there is a very large market, and people talk about the bottom of the pyramid, about the huge number of people who lack access to water but also do not have money. So there's a lot of activity, inventions to deliver water to people for very little money, especially in terms of operating costs. Because that's where I think the rubber meets the road. There are a number of, say, foundations or programs that can buy relatively inexpensive devices. I'm not talking RO, because that's probably too much of a energy consumption and high tech, but other devices, solar devices like you mentioned. But then the operation is an issue. So this is a big challenge. How do you recover these costs? On the other hand, just to mention it, there were studies done by Stockholm Water Institute that showed that people in the poorest countries in the world, and the poorest of the poorest people, pay 10, 15, 20 times more for water from street vendors than they would pay if they had a municipal water supply. So for them, water has extremely high value. And the question is, can you somehow tap in a socially responsible manner in that market? I don't know, but we have a lot of people on campus here with the Bloom Center looking at that.
I'll touch on it. There are a lot of decentralized systems. I mean, you put up a bunch of the vendors up there, whether that's a GE or a whole series of folks that have got smaller scale systems. So the challenge is, how do they get energy to those systems, and also knowledge transfer. These are complex systems. There are some package units out there that are solar based. Again, you know, if you're running at, I don't know, 300 kilowatts, you need to have a pretty big solar field for a small application, because you're dealing with higher pressure than you would normally do from just pumping the water. There are industry associations, Water for People, sponsored by American Water Works Association, that tries to get out to the developing countries and donate both time, materials, and effort to see that type of application.
Dean Kamen has his little portable methane digester and water still, and it was one of the technical he's an inventor on the East Coast who does all these wonderful things, did the segue, but he had a challenge of how do you do in a developing world where you don't have an infrastructure, you don't have electricity, you don't have natural gas, how do you purify water? And he realized that the contaminations were so diverse that often you had to get rid of arsenic, or you had to get rid of, you know, bacteria, you had to get, you know, rid of the salt, and the only thing that was universal was actually thermal distillation. And so he built a system to do that. And it's almost all a capital thing, but it's difficult. You have to have somebody trained in running it, and so then it becomes a social.
The other thing we see out there is some of the developing countries, they may, like for instance in Ecuador, there's a very large refinery that's going to be built about 20 miles away from a population center that does not have what I consider adequate sanitary and potable water resources. What typically happens is once the desal plant for the refinery is in its planning stage, then the municipality puts political pressure to carve out a certain percentage of that output or increase the output so that the municipality is getting water and the industry is getting water, and that's just kind of the fact of life.
Let me give you some, the specific, okay, you asked about the underdeveloped. Again, 40 years ago, only the rich people could afford it, in Saudi Arabia and Kuwait, or the islands for tourism. Today, about 40% of the plants are being built in places like Chennai or North Africa or in East Africa. So it's about 40% today. And what you have is women going to the plant and they buy the water. So how much is 70 cents per cubic meter? That's about, you get about 14 liters for a penny. For American penny, you get 14 liters. So the women go buy the water and then they resell it at retail. They sell it by the liter, and they make a business out of it. So, and it's very good drinking water, and the local health authorities check it, and it's actually, people are actually healthier.
That's a very interesting point. You know, the whole water market, a small quantity water market in the third world is quite an interesting field, not just the source of water and the cost, but the health aspects and a lot of other issues. So that's very interesting. We have a question over here, and then there was someone back here. Yeah, so you'll come after this gentleman, right here.
So I'm curious as to how long it takes for technology to make it into this industry. And I can see it at 3 different points. So one could be a drop in technology, such as NanOasis membrane, dropping into an existing format for a plant. And then at a second level, it might be like ERI's technology, where you have a system, you have to change it slightly to get that technology in there. And then at a third level, if you're completely reinventing everything from the start, so I don't know how many opportunities are out there in terms of that for desalination, but how long would it take to bring something complete, like moving from multi-stage flash basically to reverse osmosis. So I'm curious, is this relatively quick process, is it very time consuming, and how that affects the venture capital proposition?
Selling to municipalities and utilities is painfully slow. Glacial is a charitable description, and so normally we won't invest in anything that sells into a utility. So I actually spent a lot of time talking to water companies and things like that as we started on our water project, and that was a non-starter for a venture-backed company. Something that required a change in regulations or something like that, possibly even worse than selling to utility. Yeah. One of the reasons that we could invest in NanOasis is because we talked to the operators of desal plants, and they only wanted a year of data, or a half year of data before they would start buying and testing them. So the time of adoption is absolutely critical in terms of the things that we can invest in. And that's another reason why we're in NanOasis and not in something.
Yeah, let me emphasize that. The only reason why we're able to capture 70% global market share because it was not the minister in Madrid making the decision because he doesn't care really how much the energy is. Really doesn't care, doesn't affect it. It was through a concession system with Acciona gets the concession, then they have to operate the plant for a couple of years. You either have a concession where it's the private sector doing it, or you have sort of like a partnership, which is the Australian model, in which they have to go in and operate it for a couple of years, and you share the savings, and it actually works pretty well. So in one way or the other, the private sector, if you don't put the right technology, you get hurt. You're forced to put the right technology. Also, there's another level of clarity or keeping everybody honest, which is the bankers usually put consultants are really smart to check everything that is put in there to make sure that it works. And then they force you. The banks are forcing people to do a pilot plant, which I don't think was done in Tampa. Again, that's one of the things that if somebody has done a pilot plant in Tampa for a year using this novel filtration system, it would have crashed, and nobody would have financed it. So, but again, that was, the system the way it is now, it works pretty good. 99% of these plants are working really, really well because the system works.
Yeah, I mean, phase one was marginal piloting. Phase two, when we came in international procurement, we had to go through piloting. But actually, that's important, and that is, if these technologies come in contact with the potable water, the Department of Public Health, for instance, in California, is all over it. And they're going to rely not only on their staff, but the outside consultants. The architect engineering community is brutal on new technologies. You know, they're going to take a conservative approach, and has it been tested for 3 years? We just had a procurement down in Hialeah, Florida. It was absolutely verboten to come in with some sort of new technology. That technology had to be in a proven technology for 3 years in order for it to be considered. And that's a huge barrier. But again, it's if you want to play, you're going to have to pay.
And getting to as the producer of membranes and cartridges, concerning the adoption cycle, we went through this kind of analysis too early on. If you have a higher permeability membrane, what's the best way to utilize that? And going through that analysis, you can lower the pressure, keep the throughput the same, or you can keep the pressure the same, increase the throughput. The conclusion we came to, and after talking with some of our potential customers, is that the lower energy angle would be easiest from an implementation side of things. Say taking some of your pumps offline, or if they're variable frequency pumps, you can just dial that back down. That's a simpler way of just taking these cartridges and having them be plug and play into an existing facility. Now, to try to re-engineer the cartridge to make them higher productivity, that's opening up a whole other can of worms. We think that's ultimately there could be some value there too, but I could see a lot of people on the outside perceiving that as having high adoption risk.
Just develop your cartridge, we'll buy it. All of us will buy it.
Yeah.
Fellow back here.
Let me make a comment. DuPont, big company with deep pockets, went into the hollow fiber. Actually, they owned the desalination market in the 80s, it's more susceptible to fouling. It needs better pretreatments, and also I didn't like their business model a lot, so they pretty much went out of business about 10 years ago.
The driver for hollow fiber is really to try to pack more area, effective membrane area, into a given form factor element. So maybe in some selected applications where the quality of the feed water coming in is better, and for applications where logistics matter, portable applications, hollow fibers would be a...
Yeah, it's the dead volume. It also vastly reduces dead volume. And so in blood, pheresis, dialysis, things like that, you use hollow fiber.
Yeah.
And in ultrafiltration and microfiltration, that's where hollow fiber is dominant, although there are some flat sheet membranes as well.
Other questions? In the back.
There's been a lot of talk about ancillary environmental impacts associated with the entrainment of marine species, deposition of brine into related marine areas, but the issues associated with energy consumption have been talked about in terms of cost, but in terms of their environmental impacts, we haven't talked much about the emissions associated with the sources of energy upon which desal plants are dependent, and how that
their social cost overall and how that's reflected in the market price for municipalities considering them as a supply option, or for regulatory agencies when considering how to permit them, particularly in states like California, where we have very stringent emissions mandates for both greenhouse gases and for criteria pollutants. I see it as really challenging from a policy standpoint to advocate for a supply option that is not only creating water quality and ecosystem impacts, but is also further degrading already severe non-attainment air quality and further impeding the state's ability to achieve its greenhouse gas reduction mandate. So for those of you who fund facilities or those of you who operate them, I'm curious as to how do you do your energy procurement strategy? To what extent do you consider RECs in procuring energy supplies for facilities that you're looking at? And to what extent does the grid mix for the area where you're looking to operate come into consideration when you're developing a new plant?
Let me talk about the Perth model for a second, because that's a good answer. There's nothing better when you're a utility, any kind of a utility, whether you're conventional or solar, to have a base load customer. Desalination plant is the size of Perth. It's a 25 megawatt base load. So I can guarantee you for the next 25 years that I will be consuming every hour 25 megawatts. So I can give you a contract, which is what they did. The utility gave a wind farm operator a contract. So here you have a well-funded utility giving a wind farm operator a contract for build 82 megawatts and sell the rest of the grid. So guess how long it took the operator to get financing? Because now you have, you can get financing for something like that in minutes. But you start with clear thinking. It starts with long-range planning and saying, hey, we're going to be carbon neutral here. And not only that, but we're going to help this wind farm operator so he can provide through the grid energy to a lot of other people. That's the way it works.
In Carlsbad, AB 32 was basically implemented on the fly. I'm not a big fan of doing regulation on the fly, but the State Lands Commission that was headed up by then Lieutenant Governor Garamendi made sure that AB 32 was implemented. So in that case, the developer had to offset through a series of measures, about almost like a dozen measures, the net increase in power consumption. When I showed the graph before, so that would have been the delta, the difference between the gross 4,400 versus 3,200 kilowatt hours per acre foot. But in that case, using variable frequency drives, offsets, solar, a whole series of different measures. Now, obviously, there was some question on whether or not the AB 32 was going to be truly vetted. I understand it has been vetted. Now we're going to see it institutionalized, not just by the private sector, if there's a private developer, but also by the water districts. It also begs the question, well, if that's for desal, shouldn't that also be applied to perhaps a new water treatment plant up in Davis? And the answer is, yeah, what's good for the goose is good for the gander. But that policy was set, so if you're interested, go into the State Lands Commission hearings and all the different handouts for the Carlsbad facility, as well as the Coastal Commission on that. And it's unfortunately it's an extensive discussion. It's pretty Byzantine.
Maybe just one extra point regarding your question. There was a study done, fairly extensive study in Spain regarding their project to transfer water from Catalonia to Murcia. And first of all, the underlying assumption was that this water has to be made available in Murcia, which is their equivalent of Central Valley. Okay, and here's, I think that's a big issue. Do we really need that water? Can we live with less water? But if you said that, their study based on life cycle assessment was that at current technology, the transfer of water that was originally planned, which was sort of a California aqueduct redux, sort of the same story, would be marginally environmentally better because of the less long-term energy consumption. But what they made an interesting point is that given the progress in desalination technology, which was a competing option, and now the government of Spain is going to implement that option, there is a possibility of making larger progress, say 5 years from now. In other sense, once you build an aqueduct, it's there for next 30, 40, 50 years, I don't know for how long. If you build a plant and you have a new type of membranes, 5 years from now, you replace these cartridges and you can make this environmentally much more friendly. So that aspect, I think, has to be taken into account.
With that, I think our appointed hour has come to end the panel, but I want to thank all the panelists for your very illuminating remarks. I found it extremely interesting and an extremely good way to end my week. Thank you so much. Now the organizers have a few more words.
That brings us to the end of the stimulating panels part of today's event. We do have a fantastic reception outside waiting for you, lots of drink and food, and a great jazz band that's going to entertain you for the evening. So definitely make your way out to the right. But before we do that, I want to take a couple of minutes here to thank some really important people and organizations that helped us put this event together. First of all, I want to again thank all the panelists that spent the Friday afternoon here today to share their insights with all of us. It was greatly engaging, and I learned a lot personally from it. Second, I want to thank all our sponsors, More Davida Ventures, Acciona Agua, who is represented here by Andy Shea, and the Energy Institute here at Haas. And finally, the organizing team, myself, Ivor Castellino, Kuros Hashemi, the president of Berkeley, and a 6-member team comprising of Morgan Levy, Lindsay Miller, Nit Agarwal, blanking out on the last name, Russ Griffith, and Christy Black. We spent about the last 3 months trying to put this event together to really get UC Berkeley here to focus on water as well as much as we focus on energy. With that, please make your way outside to the right. We have a great reception waiting for you, and have a fun evening. Thank you.